Okay, now this question is to do with working out a structure and then doing some tests to identify those structures. There's 5 possible isomers following the description here, and in a lot of these questions it really is a little bit of trial and error. So we've got one OH group, saturated, that means there's no double bonds present, at least one carbon branch. What that means is there's possibly a methyl or ethyl group coming off, and there's no ring. So let's see if we can work those out. Okay, now if we draw 3 carbons in a row, that's a minimum number where we're going to have a side group coming off, a methyl group, so we can do that. And just another one coming off. And then obviously it doesn't matter if we put this OH here or here, effectively it's going to be the kind of same group, and we have a CH3 there, so that's one possible structure. Now there's only one possibility with 3 carbons in a row like that, and so then we're moving on to one with 4 carbons and the required alkyl chain, which is the methyl one. Now we can, for this one, put an OH here. Now obviously we can shift that methyl group to some other positions, sorry, not the methyl, the OH group to some other positions to complete it, but at the moment we'll just do it this way. And that's another one. Now you'll probably find as you name them that that'll help you to not miss any out. So naming this one, for instance, the alcohol group's on the first one, and there's 4 of them, so it's butan 1-ol. And this methyl group here is on this one here is on the second, so that's 2-methyl butan 1-ol. And here we've got 1, 2, 3. We've got propan 1-ol, and it's 2,2-dimethyl propan 1-ol. Although the reality is, of course, we could just call it dimethyl propanol, and that would be okay as well. Okay, and in this structure we're just putting the OH group and the methyl group on the same carbon, and so that's butan 2-ol. Oops. Butan 2-ol. And we've got a methyl group of the second one as well, so that's 2-methyl butan 2-ol. Okay, and in this one we've got alcohol group there, so it's butan 1-ol. And the methyl group's now off third carbon. Okay, and this one, which is got butan 2-ol. Butan 2-ol. And we've got the methyl group of number 33 there. And so that's the only 5 that you can really come up without repeating them. And that's the first part of the question. Now for the rest of the question, we're being asked to basically tell them apart, making some assumptions in here, that you've got certain reagents, and that once you've perhaps done a reaction which converts it to another product, that is completely different, that we'll be able to isolate that, and that any compound that has an asymmetrical carbon or a stereocenter and it's present as a single enantiomer, so a left or a right or a clockwise or anti-clockwise, and that can be detected by passing plain polarized light through it. So in other words, we can identify the products. So let's have a look at the 5 different ones and what we can do with them. Well, the first most obvious thing when we look at these is we've got some of them that are primary alcohols, one that's tertiary and one that's secondary. So if we decide to use something like dichromate, I would expect a colour change with the first two, these, and the last 3, but for this one there'll be no colour change, and the orange will stay orange as it's not oxidized, and you should make a statement to that effect. So that one's not too hard to identify, number 3. So I've just removed that to make it easier to concentrate on the remaining 4. And the fact that we've been told we can we've got a way of telling optical isomers apart, that should be really a big clue. Now, also, obviously, if we do react these with dichromate, so if we use CR, just a minute. So if we do use dichromate with these, the primary alcohols will obviously become, acids, whereas the alcohol will turn into a ketone. So any reaction, so if we're testing the products of these, which we're told we can tell apart, then the acids will obviously have acid type reactions, whether that be with metal like magnesium, we'd expect to see some bubbles, or a carbonate, that would be perhaps easier, or if you added a carbonate to it, it would react, or if you had some kind of litmus paper or some kind of test like that, where you could actually tell it using that. So as long as you've got some clarity behind that, so for instance if it doesn't react with carbon dioxide, you don't see any bubbles, etc., whereas all the others do, that means number 4. So we're going to remove that one now. Now this is where it gets a little bit tricky to tell these apart. Now because of, we look at this number 5, these two methyl groups on top of this carbon, there's no hydrogen there. If we were to try and remove this OH group and an hydrogen adjacent to it, we couldn't do it because there is no hydrogen adjacent on the next carbon, but there is on the first two. So if we do an elimination reaction and produce a double bond, and then we do a standard double bond test, which is adding bromine water, and we would expect it to go from orange to colourless, that would happen in 1 and 2, but it wouldn't happen in 5. So we've got to figure a way to make a alkene here. Now there are a couple of ways of doing this. We could, because there's an OH here, add SOCl2 is usually the best reagent, but PCl3 and PCl5 are possibilities, but usually SOCl2 will be better because it tends to form a product that's easier to separate. And if we made haloalkanes and then added KOH alcoholic, we could then basically form a double bond, and we could then test for that double bond. This would not work in this case down here. Having said that though, this would form a haloalkane there, that would substitute in that case. Alright, now so that gives us a way of identifying 5. Now finally the last two. In some respects this is the easiest. In this case, if we were to look at that carbon, it can't be the chiral carbon. This can't be the chiral carbon because there's 2 methyl groups here. This can't be a chiral carbon because of the 2 H's, and neither can this be the chiral carbon on the end because 2 H's, etc. Whereas if we look at this has optical activity because this has got 1 group here, 2 groups here, 3 groups here, and 4 groups there. And that means this is optical activity. So if we can tell them apart because of one having an asymmetrical carbon or stereocenter, as they say, that would tell you this one, and that would mean you'd be left with this one here. And that's that question.